Sorry, we're starting record here. We're about to work on lab number 11, the twin paradox. For anyone just joining us, oh shoot, now my phone is acting up. Okay, wait. For anyone just joining us, all you're going to need for this lab is a pencil and some paper and your Casio calculators. Okay. So here we are, we're set up to go. We have at the top of our page our name, lab number 11, twin paradox. You're just going to need your Casio calculators and a pencil and your brain. Okay, Nathan, ask your question away.
Oh, I was gonna, this might be like too big of a question or a simple question, I don't know. I just remembered that I like kind of asked myself this question like when I was younger. You know how like there's like a sonic boom when you exceed the speed of sound?
Yep.
Right?
Oh shit, light boom?
A light boom?
Yeah, the light boom.
Well, it
What
turns
is
out
badass?
for reasons that you're going to discover, there's a real difficulty with going faster than the speed of light. And of course, that hasn't stopped people from imagining such abilities like in Star Trek where they go to warp 1 or warp 2 and they travel faster than the speed of light. It's a colorful idea, but it turns out that you break a lot of awkward limitations when you hit the speed of light. Time shrinks to 0, lengths disappear, and you require infinite amounts of energy. So although in Star Trek they imagine some kind of a light boom where you see all the stars kind of go flying past and they make some cool effects, in reality we do not believe it is possible to travel faster than the speed of light in our current understanding of physics. One day that may be broken, and I sure hope it will, but until then, it's hard for me to say there would be a light boom when all of my understanding of physics states that the speed of light is an absolute maximum you can travel at. So that may not be a satisfying answer, but it's the best I've got.
No,
Anyways,
that's good.
I think the exploration of the twin paradox will help here. Okay, let's see if I can go sideways on my screen. I'm just going to kind of hold this up. Okay, so relativity has a number of consequences. Sorry, I'm just trying to figure out how to stationary this camera without ruining things. So we explored one of the consequences of special relativity today, of SR, shall I say. One of the consequences of special relativity is an equation called time dilation. And time dilation says this: the time measured by some observer, let's call that, oh shit, this is what I was worried about. Okay, the time measured by some observer, like observer A, is going to be equal to the time measured by an observer, observer B, divided by this special relativity whack factor of 1 minus your percentage of the speed of light squared, okay? And time dilation basically means moving clocks run slow. There are other consequences of special relativity that I did not have time to derive today, but I'll do them, well, I won't derive them, but I'll just try to justify them on Thursday. One of them is called length contraction. And length contraction is kind of interesting. Length contraction says basically that moving rods or rulers shrink as you travel at a faster speed. Let me actually show you a slide from my slideshow to help with that here. Imagine that I have where's my damn relativity slideshow? Imagine that I have some rocket, and that sitting on a platform in space where the rocket is not moving. What the shit? Oh, hold on. Sorry. Function F526. Okay. Imagine I have some rocket whose rest length is something like 25 meters. That's the length of the rocket. Length contraction teaches us that if you accelerate this rocket to some high percentage of the speed of light, here you see it traveling at 87% of the speed of light. Here you see it traveling at 99.5% the speed of light. That the measured length of the rocket will actually shrink when the rocket is in motion. And this formula is called length contraction. Moving rods or moving rulers contract in the direction of motion. Now the equation that specifies this just a moment, class. The equation that specifies this looks like this. The length of a rocket measured by observer A, who you consider to be on the train platform, is the length of the rocket measured by observer B times that same relativity whack factor that we saw before. The square root of 1 minus V over C squared. You're going to discover that this term, the square root of 1 minus V over C squared, appears in almost all formulas dealing with special relativity. So much so that sometimes people like to get this part of the calculation out of the way first because you have to do it so many times. Did you guys see how it took us a few moments to punch that in a minute ago? And it like took a little bit of work. We made a couple of mistakes. For this reason, it's sometimes common practice to invent something in relativity called the boost. And the boost gets its own variable in relativity. We call it gamma. And the boost is your special relativity whack factor. It is the factor by which times and distances become whacked out as you move closer to the speed of light. And the equation for the boost looks something like this. The boost is defined as 1 divided by the square root of 1 minus V over C squared. Okay? There's your boost right there. Now, if you define gamma in such a way, and just kind of go along with me for a second, gamma will always be a number that's equal to 1 if your velocity is slow. But if your velocity gets greater than 20% the speed of light, the boost will get greater and greater. It'll become 1.2, 1.5, eventually 2, 3, 4, 5, and the boost will get closer and closer to infinity. But the boost is always a number which is greater than or equal to 1. The boost is your relativity whack factor. When your velocities are slow, there's no difference between times measured by different observers. But as your velocity speeds up, the boost will get greater and greater and greater. One of the reasons people like the boost is they can rewrite their equations for time dilation and length contraction in the following way. Time dilation looks a lot simpler. Observer A's time, I'm all screwed up here. TA's time is the boost multiplied by observer B's time. So that's how we write time dilation in terms of the boost. And then here, the boost, oh my gosh, guys, where are my words? The measured length of a rocket or a ruler measured by observer A is the rest length measured by observer B divided by the boost. So these are our two equations for special relativity now in terms of the boost. Okay. In the following problem, where I walk you through a classic explanation of the twin paradox, we are going to start by first calculating the boost, and then we will apply our formulas for time dilation and length contraction. Let's see how this goes. Okay. Here's my twin paradox in a nutshell. At the beginning of my story, I'm going to have a pair of twin brothers who start a rocket ship company and attempt to take a rocket journey to the nearby star system of Alpha Centauri. So here I'm going to draw a sphere to represent Earth, okay? So here's Earth. And I'm going to have one brother who's a stay-at-home brother. He's the businessman who runs the numbers for the spaceship company. So here's his briefcase. And we'll call the businessman observer A, okay? He's the twin brother A. And he's going to have his twin brother be the rocket ship pilot for this brand new rocket ship, which can travel at a high fraction of the speed of light. This brother is much happier because he actually gets to ride the rocket ship instead of working out the numbers. And this is going to be brother B. And brother B is going to take a trip to the nearby star system of Alpha Centauri. Do you guys remember how far away Alpha Centauri was? I'm sure somebody knows how far away Alpha Centauri was.
4.4 light years,
Really?
I think. I don't know.
You guys don't know the distance from Earth to Alpha Centauri?
4.4 light years.
You have to unmute yourself, Anakin. Did you say something?
I'm
She said
I'm not
4.4 light
muted.
years.
at least on my screen. Can you hear me like this?
Anakin, I can hear you.
No, I can't hear
Okay.
you. Did
I
you
can
actually?
also hear you.
Actually, it doesn't show you
She
muted.
said 4.4
Huh.
light years.
Well, for some reason, I don't have sound from you. Do I have sound from anyone? Could someone talk to me?
Can you hear me?
Yeah, what's up?
Hello?
Michael, I
Ever
can't hear you
Shout
either.
into the
Are you
void and
talking?
hope that the void can
Riker?
hear you.
What am I doing here?
Hello?
Is it because I'm in share mode? Try talking to me now.
Hello?
Oh,
Howdy.
what's up?
Uh,
What's
It-
poppin'?
could you hear me?
Hi. Yes.
Yes.
I had hit
Yeah, I can hear you.
when I hit function F5. Unfortunately, on my computer, the same button to go to full screen in your slideshow is also the mute key. So you guys were all totally silent. So if you said anything to me in the last 5 minutes, I totally didn't hear it. Sorry about that. Okay. How far away is Alpha Centauri?
4.4 light years.
Okay, thank you. Jeez Louise. Let's share my screen here. I'm going to try to go through this quickly, guys. I know you've got other things to do with your day. Well, in theory, we do. The reality is that we probably have nothing to do with our day. Okay, here we go. Okay, so it's 4.4 light years is the distance from Earth to Alpha Centauri here. I should try to, not that that's going to help you much. All right. We are going to attempt to describe this journey from Earth to Alpha Centauri using the equations of length contraction, using the equations of time dilation, and using distance equals rate times time. Now let's say that these brothers are twins, and they're precocious twins who start their rocket ship company at 25 years old. Okay. The first question I'd like to ask the crew is this. Question 1 is going to be, if the brother travels at a rate of, let's make it a nice zippy rate, of 95% the speed of light, okay? So our velocity here, if the rocket ship could travel at 95% of the speed of light, how long would it take brother A to see the rocket ship take a one-way journey from Earth to Alpha Centauri? So question 1 is, how long is the one-way trip to Alpha Centauri? But we're going to say, how long is the one-way trip to Alpha Centauri according to brother A? Does anyone know how you would do this problem? To calculate the length of time it takes observer B to travel from Earth to Alpha Centauri. You know the velocity, you know the distance. What formula
Yeah.
do I want there?
Distance, wait,
Yes, say it, Mike.
it's distance, divided by time. Nope, speed.
Oh, well, what's the usual version of the formula? You've got the right idea.
Speed equals distance divided by time.
We're not solving for speed, we're solving for time.
Yeah, so we know speed, so
Or
then
can we just start with distance equals
uh,
rate times
it's-
time?
oh, is it speed times distance equals time?
Okay. It's
Velocity?
distance equals rate times time, right? And if you want to solve it
Yeah.
for time, which is what I think you were trying to do in your head,
Basically, distance divided
Yep.
by the velocity.
distance divided by the velocity. Very good.
Thank you.
Okay. Thanks, Morgan.
Having a senior moment.
That's okay. Now, what's the distance? The distance is 4.4 light years.
Professor, can you like move up a little bit? I can't really see.
Move what up?
the
You have to
phone.
be more clear
The
about your
camera.
You can't see what I'm doing there?
Phone.
No, I'm just trying to read everything on the paper.
No. It's hard because I have to like hold it up in the air and that makes it less steady. Is that better?
Yeah.
Yeah, I got to give you,
Thank
this is
you.
like notes on the board. I got to give you time to catch up to me, right?
Yeah.
Yeah.
All right. If I had like I wish I had a camera mount or something. This would go a lot better. I didn't put a lot of time into thinking about my camera mount, and I kind of regret that now. What's the velocity? %95 the speed of light. Now, how should we solve for this then? We actually want to get a number here, so what do we have to do? I want to talk about units, class. Oop, shit.
I don't even know what you have in your.
I just dropped the phone, guys. I'm sorry.
Isn't it light years? You might want to check.
Yeah, well, our distance is light years, so what are we supposed to do then? Come on, guys, you know this stuff. This is just unit dimensional analysis stuff.
I'm sorry, I'm still writing stuff.
Oh, okay. Well, I can only hold this up for so long, so let me just, I'll sip some
All
ice.
right, well, I just got it, so. If you want to rest your arm. All right, do we have to keep it as light years and as 0.95 C?
I want you guys to
Light
tell
is,
me the
yeah,
answer
that's
to
all
that.
light. Yeah, all right.
What
yeah,
units
all right,
should
hang
we
on.
use for C? What is the value of C?
So that's the speed of light.
Which is what?
Rounded or just straight?
How about to 10 decimal places, since you're asking?
Isn't it
I'll
showing
take
there's
fucking any
several
number,
seconds?
any fucking unit. Just
Isn't it
anything
showing
besides
there's
big old
several
confusion.
I know it starts with a 3.
You need hips to have a belt for it.
Thank you.
It's part of your hips.
So what do I do now?
All right, you have to find 95% of that number.
Hold on. This is where I want you to slow your roll. If you find
Okay.
95% of that number, you've got to measure time in seconds and distance in kilometers. Is that what
Oh,
you do?
you got to make it all years.
Well, that's my point is, not only do we have to make, we want our answer to come out in years, right? We want to know how many years it takes to
Yeah.
get to Compass Centauri. Also, we would like to
Yep.
measure our distances in light years. My point being,
Yeah.
this would go a lot faster if I knew what the speed of light was in light years per year. I could do this job a lot better, a lot faster. Class, what do you
Probably.
think the speed of light is in light years per year?
1.
That's right. Very good of you. The speed of light, by its own definition, travels 1 light year per year. And that means our velocity of 95% the speed of light is quite simple. If we do it in light years per year, you can just ignore the C and make it 0.95 light years per year. Now distance equals rate times time will be very simple. And the time measured by observer A is just 4.4 light years divided by 0.95 light years per year. What's that give us? You guys want to punch that in to Mr. Calculator for me? So this is a collaboration?
Yeah. 4.6.
I
4.6.
also got that. No, 4.6, yeah.
Years.
Good. So when brother B gets to Alpha Centauri, how old will brother B be relative to, or how old will brother A be? How
29.
old is brother A?
It's 29.
Yeah. He's, or if you round it to 5 years, maybe even 30, right?
Yeah, depending on.
He's almost 30 years old. Okay. How old will brother B be?
Also 29, but younger.
Wait, also 29 but younger doesn't make any sense if you think about what.
Well, 29.
No,
Because you rounded it to 30. But isn't he younger having flown?
He'll be 30. They're twins.
no. Brother B
No.
will not be 30. Even though they are twins, brother B is in a moving inertial reference frame at a high percentage of the speed of light. The concept is that brother B is going to experience time dilation. Let's answer our next question. How old is brother B? The concept is that brother B will experience time dilation. His moving clock is going to run slow by a factor of gamma. So our equation is TA is equal to gamma TB. Okay? Let's first calculate our boost. Our boost is 1 divided by the square root of 1 minus 0.95 squared. You guys want to see if you can do that without my help first? Let's see if you can handle it. It would be cool if you could just do this and then we can move on, but I might have to show you how to plug that in. What's your gamma? That sounds plausible to me, Morgan. Let me just try it out.
Your alcohol imbibing.
1 minus 0.95 squared equals square root 1 over x. Yep, Morgan, that's what I get as well. Did you guys all get that? Or
Yep.
do you want to see how to do it if you didn't? I don't want to lose anyone here. Did you guys get that?
Can you show me, please?
Yes, I would love to. Okay, let me set up my computer. Let's do it nice and slow. So let's talk strategy. I'm going to explain my strategy before I do it. I am first going to do 1 minus 0.95, and I'm going to square it, and then I'm going to hit equals before I square root. So let's do 1 minus 0.95 0.95 square, that squares your 0.95, and then I hit equals. So that's everything that's sort of inside here. Now I'm going to apply the square root. So shift square root, and I get 0.31. Now 0.31 is on the bottom. I have to flip this and do 1 over x. I'm going to use my reciprocal key so I don't have any rounding issues. My reciprocal key is here. I have to hit shift first. So I do shift and then 1 over x. Did that work for you, whoever you was?
Yes, thank you.
Okay, great. Was that Ellis?
Yeah.
Okay, sorry, it took me a second to recognize your voice without your face.
Ellis. Not
Ellis?
S3.2.
All right. Everyone else is cool with that? Okay. All right. Now, the nice thing about calculating the boost is once you do that once, all the math becomes very simple. If TA is equal to gamma TB, the time measured by B is TA divided by the boost, divided by 3.2. And TA was 4.6 years divided by 3.2 is equal to what?
$1.4.
Huh.
Hello, can anybody hear me?
Yep.
Yep.
Okay. Because I said it and nobody responded.
Oh, I didn't hear you. I can hear you now. I didn't hear you at first.
I've been saying a bunch of stuff and nobody's been acknowledging me.
Riker, we would never intentionally ignore you. We'd only accidentally ignore you. So, wait, where are you? I don't even see your face, Riker.
I'm here, I promise.
Oh, there you are. I see you now. Okay. Yeah, something must have
Raph is
happened to
also
your
here.
headset there, buddy.
Hmm.
Okay. So Bella, are you still with us, Bella? Because I heard you chime in before.
Yes.
Bella, how old is the twin brother actually going to be when he gets to the star?
Like 26, 27 years old then.
He's going to be like 25 plus 1.4 years. He's barely going to be 26 or 27 years old.
What I was trying to say was, didn't we just do the formula for length contraction, not time dilation?
No, we did time dilation because we were measuring times. The problem is we had A's time first, so we had to solve for B's time. Yes, it kind of works out like length contraction. Length contraction and time dilation are related to each other. That's going to be one of the purposes of the exercise.
Okay.
Just bear with me here. I'm trying to go through this quickly, but also make it understandable. Those two things do not always go hand in hand, right? Can everyone see that the brothers will not be the same age?
Yeah.
Yes.
That's
Yes.
weird, okay? Here's another thing. How long does brother B travel according to A? So let me just ask the question in this way. I want to say, how far is Alpha Centauri according to A? This is a very easy question because observer A is in the same reference frame. Okay. Class, in reality, Earth is moving around the sun and Alpha Centauri is also moving with respect to the sun. But let's just pretend for a moment that Earth and Alpha Centauri are fixed. They're fixed coordinates in space that don't move. A is in the same reference frame as Earth, but you could also imagine stretching a solid rod from Earth to Alpha Centauri, and that rod would measure the distance from Earth to Alpha Centauri. That rod is in the same inertial reference frame as observer A. So according to A, the length of the distance between Earth and Alpha Centauri is just very simply 4.4 light years. According to B, however, it took him a lot less time for him to travel from Earth to Alpha Centauri. He has not aged as much. Now you might wonder, if I'm observer B, will it feel like time is running slower? No, no, no. Time would seem to pass normally for the observer inside the spaceship. The way that B would see this whole thing going down is, instead of B measuring a distance of 4.4 light years, B would see the distance from Earth to Alpha Centauri as contracted in space by the effect of length contraction. So if A sees the static distance of 4.4 light years, let's ask a new question. How far is Alpha Centauri located according to B? Here's where we're going
Is
to
that
apply.
1.4 light years?
I think so, yeah. So it's okay. Let me make sure I don't screw this up.
All right.
The way the length contraction formula works is the observed length is the so-called rest length divided by the boost. And I don't want to put A or B here. This is the observer. And the rest length is the length of the rod if you are in the same reference frame. In this case, the rest length is A's length. It's LA divided by gamma. So it would be 4.4 light years divided by 3.2. Is that how you got your answer, Michael?
I just took the amount that he'd lived and made that distance.
The amount.
Like
No.
it took him. He
not
aged
traveling at
1.4 years on the.
Well, okay, you got lucky there because he's traveling really close.
I did get lucky. I'm very aware.
Okay, but you're supposed to use length contraction. You're supposed to use the distance that A observes divided by the gamma.
Yeah,
And that
I
comes
do
out
that.
to be about, if you round it out, 1.4 light years.
You can't see it, but my hands are in the air.
Oh, okay. Yeah, I see your hands in the air. Like you just don't care.
Oh, well, no.
Okay. Are you guys ready for the messed up part? You haven't even gotten to the messed up part yet. So notice that A
No.
and B both have different experiences of time and length during the trip. According to observer A, the trip took 4.6 years. According to observer B, the trip takes 1.4 years. According to observer A, the distance traveled is 4.4 light years, excuse me. And according to observer B, the distance traveled is 1.4 years. Well, this is kind of a cool result because it suggests if you can travel at high percentages of the speed of light, the distances between the sun and other stars will become contracted in that moving reference frame. Now I'm going to ask you a really weird question. Here's Earth with brother A. And here's the star Alpha Centauri. And let's imagine that brother B suddenly gets to Alpha Centauri. Here's where the essence of the twin paradox comes in. Brother B is traveling at a velocity of 95% of the speed of light. Suppose brother B takes out his super duper telescope and he looks back at his brother on Earth to try to see how much time has elapsed in brother A's frame. I'm going to write down the question because the wording of the question is important. How much time has passed on Earth according to brother B. This all goes over a little better on a dry erase board where you can see everything. Hey, my cell phone is frozen here. Oh, okay, here we go. How much time has passed on Earth according to brother B?
Wouldn't it be 1.4 light years because it's the light
wait.
that's coming off Earth is just as old as
Nathan, I got to stop you. Time cannot be measured in light years because light years is a distance. Time can be measured in.
So wouldn't it be 1.4 years?
No. I
Okay.
agree that the time measured by observer B is 1.4 years. That's how long B claims the trip took. We calculated that earlier, right?
But
Is
if
it
you can,
4.4 years?
4.4 is the distance.
Or
Please do not confuse light years and years. It's very easy to do that.
No, I was wondering if that's how much time passed on Earth for him.
Okay. We need to have a statement of the problem so you can understand what's going on. Do you guys remember earlier how we talked about the principle of relativity and how I showed you the top secret train gag where Val Kilmer was in the train station and the train cart was moving away from him? According to brother B, who's traveling at a constant velocity, remember, according to the principle of relativity, if you travel in an inertial reference frame, can always assume that you're at rest and that actually it is Earth and the distance between Alpha Centauri and this whole coordinate system, that it's actually Earth traveling past him at a velocity of 95% the speed of light. According to brother B can consider himself at rest, and he considers that observer A and the Earth and Alpha Centauri are all traveling past him at 95% the speed of light. That means brother B is going to see a time dilation effect happening on A. In effect, when we write down the time dilation formula, we write it in the following way. The observer time is equal to gamma times the rest time, where the rest time is the time an observer experiences if you are in the same reference frame. Basically, in this case, we have to plug in observer B's time of 1.4 years into the observer time, and we have to calculate a time that would be measured at rest to observer A. Basically, we're going to flip our TA and our TB here. And the answer that we would get is 1.4 years is equal to 3.2 times the time that B observes to pass in observer A's frame. Or in other words, B will observe A to have only aged by 1.4 years divided by 3.2.
0.44. 0.44.
Years. So how old does brother B think brother A is when he gets to Alpha Centauri?
Still 25 years old.
He's still 25 years old. In other words, each brother thinks the other brother is the younger brother. Brother A thinks he's 30 and brother B is 26. Brother B thinks he's 26 and brother A is still 25. Welcome to the mindfuck that is the twin paradox. The essence of the twin paradox is this. When one of the brothers turns around and comes back, which brother is going to be the younger brother? Suppose we multiplied all the numbers by 2 for a round trip ticket. Both brothers are 25 when they leave. Brother A thinks 5 plus 5 or 10 years has passed. Brother A is going to believe he's 25, and he's going to think his brother B has had 4 years elapse, so his brother B will be 29. But brother B, while he agrees that he's 29, will think only 2 years or 1 year has elapsed, and he'll think his other brother is only 26 years old. Each brother sees the other brother as being younger. So the nature of the twin paradox is to ask the question, what will happen when brother B gets back to Earth?
Would it cancel out and they'd both be the same age?
Now he'll see his brother is actually
No.
older.
Usually
Yeah.
the simple answer to the question is brother B will experience the time dilation because brother B is not in a clearly inertial reference frame. In order to go back to Earth, brother B has to actually turn around and go the other way. That means he first has to decelerate from 95% of the speed of light, and he has to reaccelerate to 95% of the speed of light there. The fact that brother B turns around where brother A does not is supposed to conclusively prove that brother B is in motion. Actually, there is a much more sophisticated answer. Oh, you guys couldn't see my cell phone. There is a much more sophisticated answer to this question than special relativity allows for. The idea of paradoxes in relativity is they're funny conundrums that come out of our usual desire to see time as being the same for all observers. If brother B turns around to come back, that seems to prove that brother B is in motion because he decelerates and accelerates. In reality, the act of deceleration and acceleration constitutes a kind of gravitational time dilation that we are going to need the more general theory of relativity to explain. Special relativity only works in domains where the speeds of the observers are strictly constant with respect to one another. The sad reality is, when brother B actually gets to Alpha Centauri, as long as brother B does not turn around, there are 3 times now. And we just have to deal with there are 3 different observers in 3 different times. There's A's time to measure for the event, which is 5 years. There's B's time, which is 2 years. And then there's B's measurement of the time elapsed on Earth, which is 1 year. The whole thing is just messed up. And there are 3 clocks and each one is valid. If brother B has to turn around to come back, that's going to require deceleration and acceleration, which will change the times in such a way. The general consensus is when brother B gets back, brother A will actually be 35 years old, and brother B will be, what, 3 years older? So 25, 26. So brother B will be 28 years old. So if you travel at high percentages of the speed of light, you can kind of jump forward in time. It's like a one-way time machine. Okay. All of this, we're going to finish up with one last problem here. What if brother B could travel at the speed of light? This will be my final sort of ta-da moment for the class, okay? Let's imagine the same problem, and let's imagine we could do, just like Star Trek suggests, a trip to Alpha Centauri at what a Trekkie would call warp 1, right? Warp 1 is where you travel at the speed of light, okay? So same setup. I've got brother A, and I've got brother B in the spaceship, but now brother B is traveling at the speed of light to Alpha Centauri, which, as you all know, is 4.4 light years away. Let's start by calculating the boost if we get to the speed of light. The boost is 1 over the square root of 1 minus v over c squared. But here, my v over c is 1.
So when y just equal 1?
Hold on. Let's do this slowly and carefully. What is 1 squared?
1.
What is 1 minus 1?
No, 0.
0.
What is the square root of 0?
0.
What is 1 divided by 0?
Oh,
Oh, can't
Wait,
do it.
no, you can.
we've hit.
Wait a minute.
Well, it's irrational, right?
No, there is an answer to this question. Do you guys remember what it was? In your basic elementary math class, they tell you 1 divided by 0 is undefined because they can't handle it. They can't handle telling you the truth. But I'm here to break those walls down, and I'm going to reveal to you the secret. There is an answer. 1 divided by 0 is infinity. Oh, that whoever had that sound button, that was pretty good.
Best timing I've ever heard.
I sure hope it's recording. We're still recording, right?
Yes.
Okay, good. Now,
Wait, this is part of the. Is this part of the lab?
yes,
Or is this
it's the
fun?
last part of the lab, and then I'm going to
1
stop.
divided by 0 is infinity.
So let's look at our time dilation formula. TA is gamma times TB. TA sees the brother B traveling at the speed of light. So how much time is it going to take at traveling at the speed of light to travel 4.4 light years? That should be an easy answer, right? What is
4
TA?
years.
4.4 years.
Exactly. Now, 4.4 years is now equal to infinity times TB. So how long does B measure for the trip to take? .4 divided by infinity is equal to what? What do you get? Huh?
Is that like some infinitely small decimal?
Yeah, what's an infinitely, think of an infinitely small number. If only there was a name for an infinitely small number.
Would it be infinity still?
No. Look, just imagine dividing 4.4 by bigger and bigger numbers. 4.4 divided by 1,000. Now let's divide it by 4.4.
Oh, is it like
4.4
it's
times
1
10 to the infinite.
infinity?
Times 10 to the negative infinite.
No, you're still missing it. If you divide an infinite number of, so say you take a piece of paper and you rip it into an infinity number of bits. How big are each of those bits?
Oh, oh, I'm sorry. I don't know, man.
Rearrange that equation.
Zero?
Yes. Something divided by infinity is 0. What have we learned?
That no time would pass?
Yeah. If you could travel at warp 1 at the speed of light, there is literally no reason to travel any faster than warp 1. Sorry, Trekkies. Because if you travel at warp 1 at the speed of light, it's instantaneous to get from Earth to Alpha Centauri. What if we did length contraction? Length contraction tells you that the observer...
What length?
Wait, isn't it
What length?
instantaneous for the person in it, but doesn't it still take 4.4 years?
Hold on, it's different for different observers. A sees it taking 4.4 years, but B sees it take 0 years. Times are dilated.
Well, that's why you would need faster than the speed of light for other people. Like if you have to bring something somewhere else and you want to get there before they all die, you'd have to go faster than the speed of light.
You're overcomplicating with too many things. If you're observer B and you don't care about your brother, you can get to Alpha Centauri instantaneously, and who gives a crap about anything else? What's the length that observer B will measure? What's
0.
the length? Yeah.
0 light years.
0 light years. What does that mean?
He took a step to the right.
Class, what it means is if you travel at the speed of light, time basically stops and you can instantaneously be anywhere in the universe. From the perspective of a photon, if such a question makes any sense, if you are Mr. Happy Photon, you literally see the entire universe length contract to a sheet of 0 dimensions in a photon's reference frame. I mean, just think about the implications of that. Let's consider what happens if we look up at the nighttime sky and we look at the Andromeda galaxy. We can see the Andromeda galaxy because we can see starlight from a distance, I think it's 2.5 million light years away. And that means when I look at the Andromeda galaxy, the photons, which left Andromeda, they left the starlight 2.5 million years ago, and they had a 2.5 million year journey from Andromeda to Earth. That's in the Earth-based reference frame. But if you were sailing or surfing on top of the photons, how long would it take you to get from Andromeda to the Milky Way?
It wouldn't.
No time.
Instantaneous.
Yeah. Think about how nuts that is. In a photon's reference frame, the entire universe contracts to a singularity-like sheet, and all lengths disappear.
It kind of reminds me of like cryogenic sleep.
Yeah, or something like that. Yeah, you're frozen in time. Now,
I don't like the existential nightmares this class gives me sometimes. God damn it. God damn it.
well, it's a happy thought because
Is it though?
we never actually get to travel as fast as the speed of light. But if we could get up to 80 or 90% the speed of light, traveling to star systems would be a doable proposition because you could get there in a few years. And that would be a long space trip, but we're contemplating a current trip to Mars. A trip to Mars at our current rate of acceleration that we can achieve in a spaceship. Oh, thanks, Morgan, for the Star Wars music. That was great.
Yeah, that's pretty badass.
I was like, is this happening? This is great. A trip to Mars at our current rate of technology. Oh, it was just a ringtone? I don't know. That was just some cosmic timing then.
It's funny. That's what I get when my mother calls.
Imperial March?
That's my mother's ringtone.
Oh, nice.
When she
So
calls
anyways,
me.
guys, you see my point.
Tell her that.
At our
She
current
already
rate of
knows.
technology, a trip to Mars would currently take 2 or 2.5 years, and we are contemplating putting humans, explorers, through that ordeal. If you could travel to Alpha Centauri in 2 years, that's a potentially doable proposition, provided you can get your rocket ship accelerated to a high fraction of the speed of light. Okay, I hope you've enjoyed our journey through time
Hold on.
dilation and length
Before
contraction.
before we finish this up, I still have that video I wanted to share.
Oh yeah, what is it again?
It's TED Ed. It's Einstein's twin paradox explained.
Okay, yeah, I also have one for advanced
I would
students.
drop a link, Riker.
Okay, sure. Why don't you share that as a link in the chat before we end here so that if people want to, they can go and check it out. Do you have that link?
I can grab it. Grab the link. Anybody who wants to watch it, I can just do it now.
Right. Well, people may have other things to do. So let's put it in the damn link because I'm going to have to stop the video at some point. I've already, okay, there we go.
It's in the chat.
Thanks, Riker.
Yeah. Okay, so I'll check that out too. There's also a very nice description. There's an advanced book on relativity that I used in my general relativity course. It's called, there's it's not supposed to be online, but it is online. It's a first course in general relativity by Bernard Schutz. Sometimes it's known to physics students as the Green Schutz book because the original printing of it was green. It's a first course in general relativity. And sometimes you can find a PDF of it online. They might have taken, oh, here we go. A first course in general relativity. I just want to show this to you because they have a really in-depth description of the twin paradox. What's kind of cool is they cover all of special relativity in chapter 1, But in the appendix, the twin paradox dissected, if you click on link 25, they have a very, very mature and advanced description of the twin paradox, where they try to get into the relativity, the general relativity aspects of the whole thing. So it's only 2 pages long, but they use something called space-time diagrams. Anyways, just think of this as a challenge if you guys really want to push yourself to the limit. I'm going to put this in the chat as well. Where's that chat log? So I'm putting that link there. If you want to read the appendix, the dissection of the twin paradox, there's another opportunity for you. I suspect that the guy who does this TED Talk,
Amber Stuver is her name.
Okay, cool. So I'll check those out. Now, a couple of you, someone just texted, Ellis asked for the notes for the first section of the lab. Should I just kind of go over those one more time before we end? I meant to have these, normally when I do this in class, I manage to somehow contain this on a single whiteboard, but I think because I was using pencils and trying to write vertically, I think this is page 1 here, okay? So here's page, in fact, who has a screenshot capability? Now do not turn in the screenshot, you gotta write this down in your own words, right? But if you wanna, Ellis, do you have the ability to screenshot? Because I can't see you.
Yeah, I'm only missing like 2 equations. I got most of it. It was just, I was having trouble organizing it, so I just missed like a little bit of it.
Honestly, that was my fault, Ellis. This is the first time I've ever tried to do this online, so it wasn't as neat and tidy as some of my work. This was the first page, okay? This is my second page, Ellis.
We can't.
Oh, sorry. Yeah, I'm not sorry. Okay. This was my first page. Did you get everything there?
Yep, I got a screenshot of it. Thank you.
Here is my second page. Here is my third page. You get that?
Mm-hmm.
Yep, thank you.
And that was my last page. That was at the speed of light. I did not expect this to take 4 pages. I think I was just kind of writing big. It was partially just a display issue. Okay. So Ellis, will that be enough for you to finish your work?
Yep, that's perfect. Thank you so much.
Just turn whatever in. If you've sat through this video and you've listened to me speak and you've tried to follow along with me, then I consider you having gone through the spiritual journey of the twin paradox.
I think in essence, if you have most of it, even if you're missing a piece or two, you're good.
Yeah, exactly. These are difficult times, and the idea is to kind of put up with me and listen to me rant. Okay, so
right, because it means that you are at least here and watching and paying it, and trying to pay attention.
Yep, exactly.
Yeah, okay. I don't like school right now.
It's Raph. Hi,
yeah.
Raph.
Yeah, I really don't like school.
This is teaching us all things that we could never have understood before, like what is the value, or what things do you gain by doing stuff in person together, right? That's something that before this would have been hard to measure. But yeah, just being in the same room, talking to people and doing it together, there's something to that, you know. You can read each other's cues, and it's ultimately about communication and information transfer. So
spitballs.
Spitballs. Yeah, we wouldn't have, you guys can't hit me with spitballs. Then again, Zoom bombing isn't possible, right? Without, so.
Professor, just remembered, almost forgot. There was something I saw on Instagram that reminded me of you the other day.
Okay.
Was it his Instagram account?
Oh, an overweight raccoon. All right, and what was the picture? Oh, look at that.
Yeah, no, I thought that was funny.
I'm trying to feed the raccoon every other day now because he's getting kind of fat.
Yeah, I told you when he crawled out.
Hey, everyone who's on YouTube watching this, buy my art. Everyone buy my art so I don't have to go to school.
Well,
Did you ever get to watch that
Follow
video I
me
sent you?
on twitch.tv/Vectorum
Okay, we're doing shout outs
If
now.
we're playing
All right,
ourselves
let's-
now.
Let's listen to the
all right,
teacher.
hold on. I'm going to stop the recording. This is getting out of control here. So let me just stop the recording before we say any more stuff.